I'm Avani Abilash, here to teach you some interesting things. Friends, do you love to study science? Yeah. Can you identify the scientist in this picture? Yeah, it's Isaac Newton. He was a brilliant scientist who have made groundbreaking discoveries in the field of mathematics and physics. He is best known for his 3 laws of motion. Isn't it fascinating to study such a brilliant mind? So, in this learning video, I'm going to teach you about Newton's 3 laws of motion from class 9 physics, chapter 3, motion and laws of motion. Friends, have you ever noticed that if you put an object in one place before you go to school, when you come back, it stays at its same position without any moving, unless an external force acts on it? Right. Yeah, like rock, motionless objects don't just start moving. When you throw a ball, it doesn't keep moving forever. It eventually stops. For a wheelbarrow to move, or a car to move, or for a plane to stay in the air, a constant force must be applied. So where did Newton come up with this stuff? Before learning the Newton's first law of motion, we have to study the different types of forces acting on a body in motion. Friends, now what about the objects on the space? Yeah, this is the kind of motion that can be seen in the vacuum of space. Satellites, stars, meteoroids, and asteroids. These objects has a constant velocity and they never stop moving. Motion in space has no friction, no wind resistance to be a normal movement. It's a motion within the Earth's atmosphere. That is the special case where objects are subjected to a variety of variables. This is why a car needs an engine that is always running, because there is resistance in the atmosphere and friction to the road. So, from the Newton's first law, we can understand that an unbalanced external force is needed to change the state of rest of a motion of an object. If so wouldn't, the object remains at its state of or a uniform motion unless an external force acts on it. Newton's first law of motion. Every object continues in its state of rest or of uniform motion along a straight line unless an unbalanced external force acts on it. This is Newton's first law of motion. And thus we can understand that a force must be applied to get an object moving and again to slow it down to stop. The capacity of an object to resist changes is known as inertia. What is inertia? Inertia of the rest is the tendency of a body to remain in its state of rest or its inability to change its state of rest by itself. So, here we have to study 2 types of inertia: inertia of rest and inertia of motion. Inertia of rest. Inability of a body to change its state of rest is known as inertia of rest, and inability of a body to change its state of motion is known as inertia of motion. So let's look some examples for inertia of rest. The first one is falling down backwards when a vehicle is started suddenly. The second one is when a branch of a mango tree is shaken, mangoes fall just as when the branches start moving. Examples for inertia of motion is: the passengers move all forward when a fast-moving bus suddenly stops. Also, a running athlete cannot stop himself abruptly at the finishing line in a race. So, by learning this, you can complete the activity on page number 49 in your physics textbook, Inertia of Rest and Inertia of Motion. Mass is a measurement of an object's inertia, whether it's in a state of rest or state of motion. As we said, this applies to an object that's already in a motion. If you get into a car accident, the force impacts will stop the car, but your inertia distracts that your body will tend to continue moving, and this is why we wear seatbelts. So Newton's first law can be also summarized as the law of inertia. Now we are moving to Newton's second law of motion. We already learned about Newton's first law of motion, which tells us that an object will continue in its state of motion unless acted upon by some net force. Newton's second law continues from there, describing what will happen if that net force is indeed present from external or internal forces. Before that, we have to learn about what is momentum. The more mass and velocity of an object, the more their impact. This property is called momentum. Momentum is a characteristic property of an object. It is measured as the product of mass and velocity. Momentum is a vector quantity. It is experienced in the direction of velocity. Momentum P is equal to mv, which means momentum P is equal to mass into velocity. Unit of momentum is unit of mass into unit of velocity, which means P is equal to kilogram into meter per second. So P is equal to kilogram meter per second. Newton's second law has an incredible range of application. It can be applied to any force that exists, and it describes the motion of all accelerating objects in the universe. We can also use it to do things like calculating faraway celestial bodies. There are a number of things that we can say about this equation. Newton's second law of motion. The rate of change of momentum of a body is directly proportional to the unbalanced external force acts on it. We already said that momentum P is equal to mv. In SI units, P is equal to kilogram meter per second. In this case, the use of this word in everyday life is fairly accurate. And we might also say that the ball rolls downhill, it will gather its momentum. This is true because its velocity will increase as the force of gravity accelerates it towards the ground. More momentum the ball gathers, more difficult. It will bring the ball to a stop. And an object in motion can therefore have a larger momentum by virtue of being more massive like a huge boulder, or also by moving at high velocity like a tiny hailstone or the meteorite falling from the sky. If we consider a car in motion, it will also have momentum equals mass times velocity. If you suddenly slam on the brake to avoid a collision, the car will skid a certain distance because force must be applied over some duration of time to bring the moving object to rest. The heavier the car and the faster it moving, the greater factor will be. A small force acting over a long time will do it. Like if you take your foot off the gas and left the friction from the road, slowly stop the car, or a large force like firmly applying the brakes to the tires. The force that's applied multiplied by the duration of time is known as impulse. It is measured in the unit Newton second. The relationship between impulse and momentum is summarized in the impulse momentum theorem. It states that impulse F delta t is equal to the change in momentum, which is delta p, also summarized as mv final minus mu initial. So, if you push an object for a duration of time, that object will gain a proportional amount of momentum. If an object loves momentum, it must be imparting some force to something else on some time period. Just as the work energy theorem describes about conservation of mechanical energy, impulse momentum theorem describes about conservation of linear momentum. Another ramification of this theorem is that the force imparted on a moving object when it strikes some surface will be very large if the impact is instantaneous, and much less if the impact involves some time duration. Friends, if you fall from your roof to the ground, it will hurt. but it won't hurt when you fall on a trampoline as much. It's because of the change in momentum imparted in your body. Instead of happening instantly, will be delivered on the entire duration of your contact with the trampoline surface as it stretches from the force of your fall. This is also happening in the baseball. Baseball players taught to swing through the ball rather than stopping the swing upon impact. Because if contact is maintained between the bat and the ball for as long as possible as maximum possible, forces will be imparted upon the ball. In the case of an object striking another object, the momentum will be conserved as the collision and the sum of momentum of two objects will be same after and before the collision. The easiest example for this concept involves ball and a pool table. We will often observe that one base has momentum while the other does not. And after the collision, the first bar has stopped and all of its momentum has been imparted onto the other ball. This type of scenario illustrates conservation of momentum. After learning the Newton's first law of motion regarding inertia and the second law of motion regarding proportionality of the force and acceleration, here we are ready to round out the trio and look at Newton's third law of motion. This is most famously stated as follows. For every action, there is an equal and opposite reaction. While this is often out of context for metaphorical purposes, in physics this means specific and quantitative. It means that if two objects interact, the forces they impact, they will be equal in magnitude and opposite in direction. Think of a car hitting a brick wall. The car impacts an action force on the wall from its motion, and the wall impacts a reaction force right back on the car, bringing it to a quick stop. These vectors are equal in lengths and point in opposite directions. What this also means is that there can never be a single isolated force, as any force is an interaction. Forces must always exist in pairs. As you sit in your chair right now, the force of gravitation is pulling you towards the center of Earth. But something called the normal force points straight up with the same magnitude. That's why you remain perfectly still. The third law can sometimes be confusing because it would seem to be implied that no object could never move since any force accelerating an object must be paired with another in the opposite direction. For this reason, we must understand that for assessing the motion of an object, we only consider the force that acting on it, but know the force it applies on the other object. Think we are hammering a nail into a piece of wood. The hammer impacts a force on nail, and the nail impacts a force on hammer. But the nail is driven into the wood because there is a net force acting upon the nail from the motion of the hammer. Likewise, the hammer has two forces operating upon it, the downward force from your arm and the upward force from the nail. That's why when you strike the nail, the hammer stops moving at roughly location where the impact occurs. So if we are looking at the nail, we only consider the force acting on the nail. If we are looking at the hammer, we only see the forces acting on the hammer. These are the different systems, and this is the context in which the Newton's third law is best understood. Let's look at another example. When a rock falls to the ground, the gravitational force from the earth causes the object to accelerate towards the earth. But it is also the case that the earth is accelerating towards the rock. This must be true according to the third law. Now we are going to complete your textbook activity based on Newton's third law of motion. Situation, action and reaction. The first situation is a man jumps from a boat to the shore. Here, the action is the man exerts a force on the boat. The boat moves backward. The reaction is the boat exerts an equal force on the man in the opposite direction. The man lands on the shore. The second one is a bullet is fired from a gun. Here, the action is bullet moves forward and the reaction is the gun moves backward. And the third one is a boat is rowed. The action is water moves backward and reaction is boat moves forward. So I hope you are able to do this activity. To every action, there is an equal and opposite reaction. This is Newton's third law of motion. Of course, we don't notice these forces in our everyday experiences, but it's very important to rationalize forces in this manner. So there you have it, the law of inertia, F is equal to ma, action reaction. That wraps up discussion of Newton's laws of motion. Thank you guys. Hope you understood everything.